So dear all, I'm Meghamala, working assistant professor from Institute of Aeronautical Engineering. And today I'm going to talk about the definitions and terminology from the gate level modeling. So far we have discussed about different types of abstraction leveling models, switch level modeling, behavioral modeling, data flow modeling and so on. And now coming up to the different terminologies and the definitions from the gate level modeling. So in the gate level modeling, the very first definition we go with this sequential logic. So what is the sequential logic is? Sequential logic is a type of logic circuit whose output depends not only on the present values of the input but also on the sequence of the past outputs as well. So the sequential logic, if you observe clearly, we see that the output may not depends on the present value of the input but also the past inputs, the history of the past inputs, history inputs and the history inputs as well. Okay, so this is nothing but the sequential logic. The outputs not only depending on the present value of the input but also the past inputs as well. Then now we will see compare synchronous and asynchronous circuits. So in this synchronous and asynchronous circuits, we see the synchronous types are pulsed or level inputs. So the synchronous and asynchronous, the basic difference if you observe the synchronous and asynchronous is, synchronous are meant with respect to time. Okay, they are pulsed. Okay, they are pulsed and level inputs. They are pulsed at different intervals of time. Whereas asynchronous are not with respect to the time constraint. And the clock input are to drive the circuit. Then with restrictions on pulse width and circuit propagation. So here in the when you are going as per the synchronous circuits, then you have to, there are some restrictions to be followed, and those restrictions are meant with respect to the clock input or the clock signals. That is a difference with respect to the synchronous. Coming to asynchronous circuit, they do not use clock signals, and so we are calling it as the asynchronous circuit. Where the synchronous circuits, they do consider the clock signals and they go as per the time with respect to time, but the asynchronous circuit is they do not use any clock signals. Then what is FPGA? FPGA is field programmable gate arrays. So this field programmable gate arrays consist of the different number of gates, numerous number of gates can be connected on one single chip, and also all the internal connections can be made using the lookup tables as well. Okay, different blocks and considerations. And here the output is observed. That means in order to get a proper output, the signal has to go through different criteria, or else it has to go through different levels. Observability, the false, it has to look false. We have to consider the false, and also by using different mechanisms, also by using different methods, we can easily find out the errors as well. So the field programmable gate array is a logic device, is a programmable logic device that supports implementations of relatively large logic circuits. So for the complex design, the complex circuits, for the large complex circuits, mostly used is field programmable gate arrays. Okay, then it can be used to implement a logic circuits more than 20,000 gates. So as I said you, for the complex designing purpose, FPGA is meant to design the complex designers. So complex designing circuits are nothing but they may use more than 20,000 of gates. Okay, then whereas CPLD can implement circuit about 20,000 equivalent gates. What is the CPLD? CPLD is nothing but the complex programmable logic design. So complex programmable logic design and field programmable logic devices, they are field programmable logic arrays. They both are one and same, but in FPGA we will be using more than 20,000 gates, whereas here up to 20,000 gates can be used in CPLD. Okay, then design flow of ASIC. So in the ASIC, design flow goes like this. The design flow of ASIC has the 8 steps to be implemented. First one is design entry, and now we have to enter the elements, the parameters, in order to design some circuit. So those parameters are nothing but the design entry, and then immediately we'll go with the logic synthesis, system partitioning. Okay, system partition has to be done based on the synthesis of the logic synthesis, and then pre-layout simulation. Okay, before simulation, we have to go with the pre-layout simulation based on the partitioning. After partitioning, we go with the pre-layout. After partitioning, each and every module has to, the layout has to be given for each and every module which is partitioned. Then after layouts, we go with the floor planning. Okay, floor planning based on the area constraint. And then after floor planning, the step we will come across is a placement. Okay, placing the components or placing the device on the particular place which is arranged for it. And then after placing, we go with the routing for the connection purpose. Okay, routing will be made to the devices which are placed, and then we will extract the output. We'll try to extract the output. Okay, the desired output we will be finding out by using different methods. And then finally, post layout simulation can be done. And now after connection, we will be able to get the output, and that output can be synthesized. After synthesizing, the simulation will be done. In the simulation process, the bugs can be identified by using different methods, different methodologies. So in order to design some complex design, or else in order to design some chip, or else any sort of design by using FPGA, the complex designers, it has to go through all this process. Okay, so all this 8 steps must be implemented. So this is the basic design flow for the application specific integrated circuits. Application specific integrated circuits design flow is all about the 8 steps, right? Then what is standard cell design? So basically we know the cell. Okay, but what is a standard cell design? How we will design a particular standard cell? So high level digital VLSI system are created from primitive components. So we know that in order to design a small circuit, we take the primitive components. The basic components can be considered from the Verilog, right? So high level digital VLSI systems. Okay, high level digital VLSI systems, they are considered, they are created from the primitive components using the concepts of repetition and structural regularity. So here, the primitives which are the primitive components which are observed from the Verilog, we use the concept mostly as repetition. So obviously, in order to design some basic building blocks, what happens is we see the repetition of the components, right? For example, gate, AND gate, we are considering AND gate. So AND gate, in the complex designing of this module, AND gate is not only considered only one time. It may consider, or else I may consider more than 10 times. That is what the repetition of the component talks about, right? So the repetition of the AND gate is considered in the one time. It may consider, I may consider the AND gate 10 times. So what happens is the component is get repeating. So that is repetition is observed. And then structural regularity. So in order to get a proper structure, okay, by considering all the components which are required to get to form a particular design, what happens is in order to get it into a proper structure, I need to consider some components, or else I may omit some components, right? So structural regularity is also one of the basic concept that we have to keep in mind in order when you are designing some module. Then standard cell design is an approach that uses a collection of logic cells to create more complex network. So in order to create more complex designings, okay, more complex modules, what we are telling is the standard cell design is one of the basic approach. Okay, by considering the standard cell design, we can easily build, or else we can easily design a complex structure. Okay, so this is about the standard cell design. Then what is a latch? Okay, so we know that latch and flip-flops, they are the storage devices. They store the bit of information. Basically, coming to the latch, they are the transparent device. So latch is a simple memory element. It stores some information. So it is very simple memory element, and it consists of pair of logic gates. Okay, so it consists of pair of logic gates because it stores some information. Okay, it may store one bit of information, and it's a transparent block as well. Their inputs and outputs are interconnected in feedback arrangements. So in the latch, by considering the by considering some gates where the output is interconnected to the integrated in terms of feedback, right? then it permits a single bit to be stored. So we know that flip-flops and latches, they store only one bit of information. Basically, if you compare the flip-flop and latches, we say the latch is a very transparent body. Get the transparent element. Excitation table. What is this excitation table is? We know the excitation table, it differs from the flow table, right? So excitation table is meant only the output is mentioned, whereas in the flow table, we see the output of the next state is also to be considered. So now we see the excitation table. During the design process, we usually know the transition from present state to next state. Obviously, in the designing process, we see A and B are the two states. Okay, we see the transition happening from the A to B. That is, this is a present state and this is a next state. The transition is occurred from the present state to the next state, and wish to find flip-flops input conditions that will cause the required transition. So based on the flip-flop that you are considering, based on the information that is passing out from the one state to the other state, we see the required transition is needed or not. Okay, sometimes what happens is we need some transition. That means the information has to pass from one state to another state. In such cases, we have the transition is to be made. If not, the transition is not required at all. So a table which lists the required inputs for a given chance of the state is called the excitation table. So here, this excitation table consists of all the inputs. Okay, all the inputs I0, I1, and also it consists of the output as well. Okay, but if the transition is occurring, then we have to represent the next state, right? So the next state can also be observed in the excitation table. The excitation table will also consider the next state, the required transition of the next state. Okay, then for going with the registers. So we know the registers are nothing but they store the information. So in the registers also we have different types of registers, and the representations of registers we may represent with respect to the numeric numbers, or else we can also represent or give the names in terms of the alphabets as well. Okay, and in the registers we can see the partition as well. Some registers may 0 to 15 bit of registers. So out of 0 to 15 bit of registers, we can divide it from 0 to 7 and 8 to 15 as well. And then registers are nothing but the group of flip-flops. Obviously, the register it contains, see, this is a register R. So this register it contains a group of flip-flops D, T, RS and D2, D1, D2 like that. So group of flip-flops can store one bit of information. So n bit registers has group of n flip-flops. Obviously, so registers are nothing but the storage devices. They store, the group of flip-flops are nothing but the registers. All the group of flip-flops are accommodated in one place is nothing but the registers. And for n number of registers, we store the n number of flip-flops in the registers. So the group of n flip-flops are capable of storing any binary information and which are containing the n bits, obviously. And then what is a flip-flop coming up? So flip-flop is nothing but it is a storage devices where normally it samples inputs and changes its outputs only at the times determined by the clock signal. So only at the clock signal the output is observed. If D is a flip-flop, D is the input, output is observed as Q. Okay, and this is clocked, or else the output it changes. The input will changes its output only at time determined by the clock signal. Only the output is observed only when the clock is determined by the output is determined by the clock signal. So in the flip-flops we have different types of flip-flops: D, T, SR. Okay, D, T, SR and master slave flip-flops as well. And then what are the value sets in Verilog? So in the Verilog, value sets are nothing but they are one of the one of the tokens that we can consider in the Verilog. So this Verilog, it supports 4 levels for where it needs to be described hardware referred to as the value sets. So we know the value sets in the Verilog as the basic value sets. We know 0, 1, X and Z. So 0 is meant for the logic 0, that is false condition, and 1 is meant for the true condition, and the X is meant for the unknown and the logic value, and Z is meant for the high impedance or floating state value. So we all know Z represents the high impedance, X represents the unknown logic value. One represents obviously the statement goes with the true, that is 1, and 0 means the statement goes with the false. Then coming to the Moore and Mealy and Moore machines. So Mealy and Moore, these are nothing but the finite state machines. Okay, so these finite state machines, the difference between Moore and Mealy goes with this. The Moore machine, the Mealy machine, the output depends on the current state and the input. Okay, in Moore machine, the output, it depends on current state, that is present state, and the output and the input. Whereas in Moore machine, the output depends only on the current state. The output depends only on the current state in Moore, whereas in Mealy, the output depends on the current state as well as the inputs as well. Okay, so in the Moore and Mealy machines, we see that these two are the categories, or they are constrained from the FSM, finite state machines. These two are the finite state machines. Basically, compared to the Moore and Mealy and Moore machines, we go as per this Mealy machine. We consider most of the times a Mealy machine, because here the output depends on the present state of the input and as well as the past output. Then, what are the various modelings used in Verilog? So, in the Verilog, we know that the basic modeling styles are gate level modeling, behavioral modeling, switch level modeling, and the data flow modeling. So, all these four modeling are present, or all these four modeling are the basic modeling styles in the Verilog. So, coming to the gate level modeling, by considering different gates, okay, in order to build some basic building blocks, we will be considering all the different gates which are present in the gate primitives in the Verilog. And then data flow modeling is nothing but the data show how the data is flowing among the registers, how the data is flowing among different transistors. Okay, it's all carried out with respect to this data flow modeling. And coming to the switch level modeling is nothing but here based on, or else by considering different switch primitives from the Verilog library can be considered, and based on the switches, the flow of the information from the source to destination is carried out. And then behavioral modeling, as it is a high level of abstraction modeling. In the behavioral modeling, not only in the behavioral modeling, on all the different stages, all the different style modelings, we are using the different keywords. Okay, here basically always at the rate is used. And the switch level modeling, basically we go with the assign, or else simply without using any keyword. There's no proper keyword mentioned. In the data flow modeling, assign. The gate level also assign we will observe. Then, what is an FSM? FSM is finite state machine. It is a mechanism whose output is dependent not only on the current state of the input but also past inputs and outputs as well. So, finite state machine. Here, these machines, the output not only depends on the present state of the output, but also the output can be observed or considered from the past state of the output and as well as the past inputs. Okay, so such machines are nothing but the finite state machines. So under the finite state machines, we have discussed about the Mealy and Moore machines. Then, what is the design methodology for sequential circuits? So the design methodology for the sequential circuits, in order to design a sequential circuits, we have to identify the distinct states. Okay, so different states we must identify: A, B, C, and D. So all the representation of state is inside the circle. Then create state transition diagram. And now we have to represent in the state by using the state transition diagram. So the state transition diagram consists of the states which are mentioned in the or represented in the circle and the direction lines. The transition, if it is taken from A to B, this is how the direction line goes. From B to C, this is how the direction line goes. From C to D, this is how, and from D to A, this is how. So by using the direction lines and by using the circles and the states, the representation. Now the first step is about the identifying the states. Second step is about the transition diagram, and the third step is about the encoding. Okay, choose state encoding. Now we have to choose if it is a complex. The considered states are looking like a complex structure. Then we have a chance to reduce it by using state reduction process. So by using state reduction process, we can reduce a complex design to a very small, comfortable design. Then write combinational Verilog for next logic. And now we have to write the combination. We have to write the code. Okay. After state prediction, we have to go with the Verilog combinational Verilog for the next logic, and write combinational Verilog for the output signals as well. And now we have to see whether the transition is taking place between the states or not. That, and also we have to see whether the output signal, based on the output signal, how the transition is taking place. So all such things can be observed when you are creating, or else when you are going to design a sequential circuits. This is a methodology. Then state diagram. So state diagram is a graphical representation of state tables. So this state diagram consisting of all the state tables. The state diagram consists of all the state as I showed you before. So this is the direction lines, based on the direction lines and the states. So this is a sequential state table of sequential, represent the state table of sequential logic. So state diagram, it represents the state table. So state table consists of A, B and the outputs. Q bar are the outputs, present state and as well as the next state. Then what is a critical race? In critical race is asynchronous circuits occur between two signals. So critical race is observed in the asynchronous circuit. The critical race is occurred between the two signals that are required to change at the same time. Okay, in the same time, if two signals, signal 1 and signal 2, if they want to change, if they are required to change its time, if there are any changes or the transition is taking place at the same time at T1 and T2, then it is nothing but the critical race. It is very difficult to identify, or else it is very difficult to get to know the delay. Okay, that's what we are saying, that it is a critical race. In order, if two signals are required to change at the same time, then this is nothing but the critical change when the next stable state is dependent on the delay path in the circuit. So obviously the present state and the next state. So the next state is dependent obviously on the present state, right? So if some chaos is been occurred in the present state, obviously the next state has to the output, the next state has to be in a waiting position. So unless and until if it is cleared in the present state, the next state output is not observed. So that is what the critical race. So the critical race maximum, most of the times we observe the critical race are present in the asynchronous sequential circuits. But whereas in synchronous sequential circuits, no hazards and no critical race can be observed. Then what is ASM chart? So ASM chart is meant as algorithmic state machines. So these are the charts. They specify the type of flow charts. Okay, these are the type of flow charts where they specified based on the transition, based on the delays, based on the output that are observing, based on the conditions as well. So these are the types of flow chart suitable for describe the sequential operation in the digital system. So based on the flow chart, in order to understand the mechanism or as a functioning of a particular state machine can be easily observed, or else they can be easily considered or written in terms of flow chart. Okay, based on the conditions and as well. So ASM charts are so and so. And then what is a cycle? So cycle is, the cycle occurs when an asynchronous circuit, it makes a transition through a series of unstable states. So when the transition is occurring in a series of unstable states, when the state is not stable, when the transition among the different states are occurring abruptly, then we see that such cycle is nothing but a unstable, when the abrupt changes are occurring in between the states, unstable state, then such kind of a loop is nothing but a cycle. A cycle occurs, the cycle occurs when asynchronous circuit, when the asynchronous circuits not with respect to time, the cycle occurs in the asynchronous circuit that makes a transition through a series of unstable states. And then if a cycle does not contain a stable state, the circuit will go from one unstable to another stable state. So here, if there is no chance of occurring any cycle, so a cycle does not contain a stable state. Obviously, the cycle among the different unstable state, the cycle process goes on. But if the cycle consists of any stable state, then what happens is the circuit will, the circuit is changing, or else we will see some change. That is, the transition is occurring from the one unstable to one stable state. Okay, and from one unstable to one stable state, and from one stable state to one unstable state. If you see a transition occurring among these such states, unstable to stable, stable to unstable, then that is nothing but a cycle. Cycle does not contain any stable state. Cycle contains only the unstable states. Then coming to what do you mean by the term state reduction problem? So state reduction problem is reduction of the number of flip-flops in the sequential circuits is referred as state reduction problem. So if the number of flip-flops are reduced in a particular state, then that is nothing but a state reduction problem, and the algorithms are concerned with procedures for reducing the number of states in a stable state while keeping the external input-output requirements unchanged. So the state reduction problem can be overcome, or else the procedure goes on like this, where the outputs are unchanged, the external inputs and the outputs are unchanged. Okay, we can reduce the number of flip-flops where the outputs and inputs at the externals are not unchanged. Then what are the rules of identifiers? There are some rules to follow if you are considering some identifiers in your code. So what are those identifiers? The list of the rules that is can contain alphanumeric, underscore characters or dollar sign. Alphanumeric, okay, alphanumeric or underscore or dollar. So this is one of the rule to identifier. Then may use any character by escaping with a black hash at beginning of the identifier and terminating with a white space. So here one of the rule is that it could be an underscore, it could be a dollar, or it could be alphanumeric. And the second one is it must have a black slash at the beginning of the statement. Okay, and then also the white space. We know the white space. White space is nothing but, for example, this is nothing but a state. In the statement, I have written block with some space. Okay, these are the space. So it doesn't matter at all. Okay, these are the extra spaces that we can give. So this is also considered to be one of the identifier, and it can be up to 1024 bytes and cannot contain white space. So as I said we may see the white space, right? So identifiers cannot contain the white space. If you have white space anywhere, if you have observed in your code, then immediately you have to omit it. Okay, so these are the rules to follow if you are considering, or else if you are writing your code in terms of with respect to the identifiers, by making use of the identifiers. And give the needs for switch level module. So what are the needs that we have to consider if you are going with the switch level modeling? Switch level modeling are used to allow detailed construction of logic gates and functions, and also to allow complex design modeling to be used. So in order to design a complex design, we are preferring the switch level modeling, because the switch level modeling by making use of different logic gates. Okay, so the logic gate, the construction of logic gates, the detailed construction of logic gates and functioning of such logic gates, in order to build a complex structure, we are making use of this logic gates and the functioning of particular logic gates. Overall together is nothing but the switch level modules. Okay, so this is all about the final module, and so far we have discussed about the ASICs, different types of the design flow of ASICs, and the FPGA, and comparison between FPGA and CPLD, and what are the identifiers, what is module, and what is the instantiation of the module. And also we have discussed about the FSM, finite state machines, different types of finite state machines, ASM charts as well, and also state diagram, about the state diagram, cycle, and so on. All these terminologies we will come across in the last module, and this is how we have to define them. Okay, we have to define them, and that is about the last module, definition and terminology. I hope you understood well, and thank you.
Like, share and subscribe. Hit the bell icon for more updates.